So, now let us understand, let us review a little bit about the microscopic definition of heat and work. So, how do you understand heat and work in terms of atoms and molecules? Okay. So, let us say I have the system. So, you know that every atom or every molecule is arranged according to different energy levels according to quantum mechanics, right. Even though classically the levels are very close together, but the energies are discrete or quantized. So, let us say I design a system, very restrictive system, where there are 4 particles, 3 particles are on the ground state and 1 particle is in the excited state. Now, total energy of this particular system is how much? 1, right. Total energy of the system is 1, because 3 particles are in 0, and I add heat to the system. So, what is going to happen? So, whenever I put heat to the system, the energy of the system is going to increase, and since we know that internal energy and heat, they are of all the same thing. So, I put Q equal to 2 means my total energy is going to be 3 now. Now, how is going to be 3? It is going to be 3 by sending some particles to higher energy level. So, here I am showing that these 2 particles, one of them actually goes to level 2. So, now the total energy of the system becomes 2 plus 1 3, 2 plus 1 3. So, when I add heat to the system, what happens is that there is a redistribution of particles in different energy level that take place. Okay. You will understand later that it is because of the Boltzmann distribution. So, you will see that particles are distributed depending on the temperature and the energy levels in such a way that it satisfies the Boltzmann distribution. However, the adding work on the system is little bit more complicated. Okay. So, what happens when you do work with the system? Actually, I should write it here. So, let us say, do you remember the particle in a box formula? Particle in a box you remember, right. So, using particle in a box, can you tell me that when you do work on the system, so we know that from the first law of thermodynamics that U equal to W when there is no heat supplied, right. I should change the color. So, U equal to W when there is no heat supplied to the system, that we know. Now, I am asking you that given a distribution of particles where let us say some particles are there in this level, the total energy of the system is now epsilon or 1, whatever you can say. If I do work on this particular system, what is going to happen? Will the particle go to the higher level? Let us say I do 1 unit of work, W equal to epsilon, let us say. What do you expect that is going to happen? Do you have any idea? What is work? What happens in work? When you do work, then the volume changes, right. Volume of the system changes. Now, imagine particle in a 3D box. So, particle in a 3D box has 3 different lengths, lengths, widths and heights, right. So, there from 3D box let us come to 1D box. So, let us say for a 1D box, if the box length changes, let us say it goes from L to 2L, what happens to the energy level? The gap between the energy levels decreases, right, they become more closer. So, similarly, when you do a particle in a 3D box, when you are let us say isotropically your volume changes such that from all different size the length changes, what is going to happen? Your energy levels now going to be more closer, and opposite will happen when you compress the system. When you compress the system, then what is going to happen is your energy levels are going to be now separated from each other, more separated, and you know the formula, right. So, E n at least for particle in a box is n square h square by 8 m L square. Now, if L becomes smaller, the difference is going to be larger, right. So, a compression work I told you is the work in which the internal energy of the system increases, because that is a positive work. So, therefore, we are going to look at compression work, we are going to look at when volume decreases or L decreases. What happens in that case then? energy separation increases. So, now when that happens, this E is going to become 2 E. So, this gap separation, so this is just an example that in this particular case when you do work up to the amount of epsilon, then instead of the difference epsilon, now the difference becomes 2 epsilon. However, the distribution of particles need not change here. Without the distribution of particles being changed, the energy can change when the energy levels itself changes. So, this way you can understand that when we heat the system, how the energy can be distributed in the system by distributing the particles, or when you do work on the system, work meaning we are compressing or expanding the box size, there the energy levels of the particle itself is changing. For example, we talk about gas particles. So, this is like a one dimensional system. We are taking an example of a 3 dimensional ideal system, and you will see that using this information that in case of work done dW, it is a constant multiplied by dE, the level itself, the energy level itself changes, whereas for Q it is your E dN that is going to change from a microscopic point of view. So, energy can be changed by moving the particles in different energy levels, or it can be changed by doing the work, we have shown that, and from the particle in a box we can understand that how changing the box length or rather box volume is going to affect the different energy levels. Okay. Here I am going to show you. So, all of you remember the particle in a box system, right, and imagine that particle in a box system, of course, there is only one particle kept, typically we discuss about one particle which can be at any different levels. However, imagine that there are many different particles are there at different energy levels. When you hit the particles, they will get redistributed in the same energy level, because we are hitting the system and assuming that there is no work done, which means that as long as the box length remains fixed, as you can see the box length remains fixed, then the energy levels itself do not change, right. So, if you hit the system, total energy of the system is going to change. However, energy levels do not change because the box length is fixed. In case of 3 dimensional box, it will be box volume that will remain fixed. So, therefore, when you hit the system, the way in order to change the internal energy, the particle distribution in the different levels will need to be changed, right. That is how we can think about a microscopic description of heat, in which distribution of the particles change. However, when you do the work, remember what we do is that we change the volume of the box. Now, here we are showing the one dimensional box, which is the length, but if it is an isotropic box of all equal sides, which means the length is changing as v to the power 1 by 3. So, by changing the length, we can understand how the energy levels change, and when you let us say compress the system, that means you make the L smaller and smaller, you see now the difference between energy levels become larger. Now, you see the difference between two energy levels is let us say 0.97 and 3.78. Now, if I make it bigger, the difference is much smaller, right. So, by just doing the work, what we are doing is that assuming there is no heat given into the system, that means the particles are in the same level where they were. However, now they are of different energy. Is it clear? Yeah. So, that is how we can understand microscopic descriptions of heat and work from particle in a box or very simplistic system itself. One can show later on that the energy that we get for a particle in a box, let us say 3 by 2 kBT or 3 by 2 n kBT, that can be also obtained from particle in a box systems as well, both from quantum mechanics and classical. So, classically it is half mv square equal to kBT, half kBT is the energy that is there, assuming there is no interaction among the particles in ideal gas systems, there is no potential energy. So, all the energy that is there is the kinetic energy, and we already discussed that kinetic energy is half mv square or v average v square average, which is half a kBT, right. So, now that is only the velocity in one direction, Now, if you now take all the 3 different directions, it will be half kBt plus half kBt plus half kBt, which is 3 by 2 kBt. So, 3 by 2 kBt is the total energy that is available for one particle in an ideal gas situation. 3 by 2 n kBt is the total energy that is there for n particles of an ideal gas. Okay. So, and the same thing you can get, and we also discussed that quantum mechanics we only get the kinetic energy, because there is no potential energy. Remember, the potential energy operator was 0. So, what was all there is a kinetic energy operator, and one can show that using this particle in a box systems, your average energy you can get as 3 by 2 kBt as well. Okay. We are not doing that right now, but it can be shown later on.